Hello and welcome to today's lesson in aromaticity. This is the Chem OG. And when we take a look at the word aromaticity, the first 8 letters of aromaticity lead you to believe that, hey, we may be looking at a compound or a molecule that is fragrant or has a smell to it. And that's kind of where aromaticity originally got its name, is that a lot of chemically, what we refer to as aromatic compounds, these compounds smell, right? Some of them are more pleasant than others, but it's not necessarily true that when we refer to aromaticity in a chemical sense that all of these molecules are fragrant. So aromatic compounds tend to be relatively very stable, not just stable, but very stable. In fact, in the off chance that aromatic compounds do react, which would be the opposite of stability, in the off chance that aromatic compounds do react, it'll actually be the case that they're going to want to tend to reestablish their aromaticity. So even when they do react, they still want to go back to being aromatic. And so how do you spot an aromatic compound? Aromatic compounds are going to have 4 properties, and they must meet all 4 properties in order to be considered aromatic. The first property is that they need to be cyclic. Second property is that they need to be planar. They also need to be conjugated, and last but not least, they have to have a certain number of pi electrons, 2, 6, 10, 14, 18. You kind of pick up on the pattern here is that we're adding 4 each time. So if they have that certain number of pi electrons, awesome. If they don't, then they're not aromatic. Must meet all 4 of these rules, not just some of them, but all 4 in order to be considered aromatic. So let's talk about each of these 4. The first rule that we mentioned was that the molecule has to be cyclic. What does that mean? It means that the atoms need to form a ring. If they don't form a ring, you're out of contention in terms of aromaticity. Rule number 2 says the molecule needs to be planar. Now, planar means that the atoms and the way they're arranged when they bond together is that they're 2-dimensional. And that's very strange because molecules are definitely 3-dimensional. So if I'm talking about a planar molecule, that means that I'm referring to something that is as flat as a sheet of paper in a world that's, in 3-dimensional space. So planar molecules have a flat structure, and it also means that we can't have any sp3 atoms, because if you remember, sp3 atoms are tetrahedral. They do, exist in 3D. And so sp3 atoms are ones that have 4 electron groups around them. Now, an electron group could be a lone pair, or it could be a bonded atom. If you got 4 things around you as an atom, you're going to be sp3, and that also takes you out of contention in terms of aromaticity. Now, I will say that not all lone pairs of electrons should be considered as electron groups. So lone pairs of electrons that are adjacent to a pi bond don't count as an electron group. So we'll take a look at an example of what that means. Rule number 3, conjugation. So how do you spot conjugation? Probably the first thing you should look for is alternating pi bonds. So you're going to have carbon atoms that have a pi bond, one next door that doesn't. The one after that has a pi bond, next one doesn't, one after that has a pi bond. And in order for that to happen, none of the atoms can be sp3 hybridized. So that sp3 hybridization, in more ways than one, takes you out of contention for aromaticity. And then last rule number 4, a lot of times the way it's expressed is algebraically, but 4n plus 2 tends to throw some students off. If you just remember it as 2, 6, 10, 14, then you're in pretty good shape. So we're looking for a certain number of pi electrons, and that is known as Huckel's rule, for a German chemist, Erich Huckel, who sadly died in 1980. All right, so let's take a look at an example of a couple of molecules, and let's see if they are aromatic. So the first molecule that we're going to take a look at is pyrrole. The next molecule we're going to take a look at is a fun one, and that is caffeine. So questions we want to ask are, hey, are these molecules aromatic or are they not? And we're going to take a look at their aromaticity with respect to the 4 rules that we discussed. So rule number 1 is cyclic. Do the molecules have rings or do they not? So let's tackle pyrrole first. And if I take a look at pyrrole, pyrrole definitely has a ring in it, so check. It's a cyclic compound. If I take a look at rule number 2, is it planar? Well, planar, that means that all of my atoms, none of them, out of all my atoms, none of them can be sp3 hybridized. So the carbon atoms seem to be in okay shape because these carbon atoms both participating in a pi bond. So I'm not worried about those. Those are going to be sp2 hybridized, and they're not sp3, so they're good. The nitrogen, though, I am worried about because the nitrogen is bonded to a lone pair, so that's one electron group. It's bonded to hydrogen, that's one bonded atom, and it's bonded to 2 carbons on either side. So we got 3 atoms to which the nitrogen is bonded, 2 carbons and a hydrogen. We also have a lone pair of electrons, so that makes 4. But remember that if a lone pair is adjacent to an atom in a pi bond, don't count as an electron group because that lone pair is capable of resonance, and that lone pair of electrons is very much capable of forming a pi bond. And so it would count as, in terms of our number of electrons that we count inside the ring. And it also makes that nitrogen, because we're not counting the lone pair, it makes it sp2. So that is a planar structure. Is there conjugation? Yeah, we got alternating pi bonds, and every single member of that ring is planar. And so how many pi electrons do we have? Well, remember, because this lone pair of electrons can participate in resonance, it means that I should count it in terms of the total number of pi electrons. So I got 2 electrons on the left, 2 electrons on the right, plus these 2 lone pairs of electrons. 4 plus 2 makes 6, and that means that I have a molecule that also obeys rule number 4. Pyrrole checks off the list for all 4 rules, and that makes it an aromatic compound. All right, let's take a look at caffeine. So caffeine has a couple of rings that are fused together. So check mark on the cyclic part. In terms of planarity, again, the thing I'm worried about are the nitrogens. So if I take a look at the nitrogen at the top left here first, I have a lone pair, but that lone pair has a couple of adjacent atoms, whether it's this carbon over here on the right, or whether it's the carbon on the left. Each of those carbons is or contains a pi bond. So this lone pair is capable of delocalization. So this lone pair right here is capable of delocalization. And so that means that that nitrogen only has 3 electron groups around it. So that nitrogen is sp2. Take a look at this nitrogen over here. It's also sp2. Take a look at this nitrogen over here. It's also sp2 because I got pi bonds right next door. Right? So in terms of the nitrogens that I was worried about, everything's planar. So check mark on rule number 2. In terms of conjugation, I got alternating pi bonds all over the place. Every single one of my atoms, is in a flat structure. So there's conjugation going on there, alternating pi bonds. And in terms of how many pi electrons we have in total, we got to count those lone pairs on the nitrogens that had pi bonds next door. So notice I'm not really accounting for this nitrogen's lone pairs because that nitrogen is already participating in a pi bond. So I'm not worried about this nitrogen because it's already participating in a pi bond. And so everything is sp2. If I count up the number of pi electrons, I'm going to count these electrons over here, so that's 2. I'm going to count these electrons over here, that's 4. These electrons over here, so that's 6. And I also have 2 pi bonds that are already in place, and that means that 6 lone electrons that get delocalized plus 4 that are already as part of the structure, I'm going to get 10 electrons in total, and that fits within the pattern of 2, 6, 10, 14. So both pyrrole and caffeine happen to be aromatic compounds, and we already know caffeine has a pretty distinct, strong smell. So caffeine definitely counts as an aromatic compound in sort of the colloquial sense as well. All right, so let's take a look at a summary of what it is that we discussed. So aromaticity is one of several ways that a molecule can stabilize itself. Aromatic compounds are really generally unreactive, or as we said, they're pretty stable. Even when they do react, they often revert back to their original aromaticity. And the stabilizers, the mnemonic that I gave you in another module, and I'll give it to you again, is raise. So each of these letters stands for one of the factors that helps to stabilize our molecules. So today in particular, we discussed aromaticity. As always, keep learning. Hopefully today's lesson in aromaticity was something you found helpful. And as always, you are welcome.